Though rooting complex numbers themselves have very practical importance, rooting real numbers is of very good theoretical importance. And of all the real numbers you could think of, rooting 1 is of the biggest importance. This is what we call the root of unity. If asked to cube root 1, in our real world you will only say this has one solution, which is then z is equal to 1. But because this is now a polynomial of degree 3, essentially a cubic, because this is equal to 1, by the fundamental theorem of algebra, we know that this is going to be 3 roots. How do we find these 3 roots? Well, we know that z equal to 1 is a root, and therefore z minus 1 is 0 as a factor. We can rewrite z cubed minus 1 equal to z minus 1 times this geometric series. So we can express this cubic polynomial as a product of a linear factor and a quadratic factor. Now for this quadratic factor, let's just put it in the quadratic formula. Putting in a quadratic formula, we see that we get 2 roots. And therefore the 3 roots to this equation is omega 0 equal to 1, now notice that the two complex roots are themselves conjugate pairs of each other because this is a polynomial with real coefficients, which is what we expect. Let's talk about some properties of the cube roots of unity. If we had the 3 roots of omega 0 to 1, omega 1 equal to if we were to sum the roots, we see that the imaginary parts knock off, and we see that 1 minus half is 0. So the sum of the roots is equal to 0. Let's take the product of the roots. And if we multiply all of this up, so what we can see from this is that the sum of the cube roots of unity, 1 plus omega squared, letting either omega 1 or omega 2 be omega, or letting any one of them be omega to cube it, we get 1. If you were to cube omega 1, you're going to get 1. If you're going to cube omega 2, you're going to get 1. If you're going to cube omega 0, you also get 1. With that said, we can actually do some questions about this. If omega is a cube root of unity, simplify 1 plus 6 omega plus 1 plus 6 omega squared. Well, using our properties of the cube roots of unity, we know that 1 plus omega squared equal to 0, and we know that omega cubed equal to 1. Expanding all of this out, immediately we know that omega cubed is going to be 1. So 1 plus 36. But we know that omega squared is going to be minus 1 minus omega. The six omegas cancel off. In trigonometric form, the same cube roots of unity is going to be by Demar's theorem, equating the real and imaginary parts. From the real component itself, when k equal to 0, when k equal to 1, but this is not in the principal domain, so we subtract 2 pi. But what is cosine I sine of 0? So these are 3 cube roots. What would they look like on the Argand diagram? Well, because all of them have a modulus of 1, they're all going to lie on the unit circle. Where is 1? Where is 2 pi on 3? Where is minus 2 pi on 3? So they're going to form the vertices of an equilateral triangle. As the cube roots of unity form the vertices of an equilateral triangle, this answers our question as to why a polynomial must have all real coefficients before the complex roots occur in conjugate pairs. For the cube roots, the vertices lie here. For the fourth roots, whoops, not there. All of the roots of cube roots, fourth roots, fifth roots, sixth roots are drawn, and what we notice is that all these roots are symmetric about the real axis. Had it been a complex number in which we are rooting, the roots may be slightly off-centered, indicating that the complex roots will not occur in conjugate pairs. If we were to factor this out, if we do it in trigonometric form instead, which is probably more beneficial, we're going to see that all the omegas are going to be written in this form. Where the counter k is always going to be n minus 1 at most. So the actual roots are going to be given by And if we keep going, but what is the relationship between omega n minus 1 and the first complex root of omega 1 instead, not omega 0, omega 1? Let's expand this. But by your double angle formulas, and omega n minus 1 is omega 1 bar, the conjugate. Because the power of n could be a positive number or a negative number, we have two possible situations happening. If n was even, there will be n minus 2 on 2 pairs of complex roots together with the real roots of plus and minus 1. If n was odd, there will be n minus 1 on 2 pairs of complex roots together with the real root of 1, which kind of matches up when we did cube roots and fourth roots. The cube roots of unity, the roots are going to be the real root and the two complex roots. And if n was odd, there will be n minus 1 on 2 pairs of complex roots. So what is 3 minus 1? 2. And what is 2 on 2? 1. There's one pair of complex roots. The fourth roots of unity. And there'll be 4 minus 2, there'll be one pair of complex roots and the real roots of plus and minus 1. We can also factor the roots of unity. Let's just take any conjugate pair of roots. Which will lead us to the factors of and this will lead us to the quadratic factor. So taking a conjugate pair and writing as a factor, which leads to factors of z minus that particular complex number times z minus the conjugate of the complex number. If we multiply it all out, because we know that a complex number multiplied by its conjugate is going to be a real number, this thing here is a real thing. It's a real quadratic factor. So again, we get two possible situations. The two situations being when n is even and greater than 2, the factors come out to be zn minus 1 can be decomposed into z minus 1, z plus 1, and a product of all these factors. And if n was odd but greater than 1, z to the power n minus 1 can be broken into all these factors as well. We know that when we rooted complex numbers, that all roots must be spaced 2 pi upon n apart from each other. Same goes with roots of unity. All roots must be spaced 2 pi on n apart from each other around the Argand diagram. Except the only difference is that now the roots lie on the unit circle. And if we have Zn, the n roots of unity, they're all gonna, as we go more and as we have n increasing more and more and more and more, the polygon that all these all these roots trace out goes from an equilateral triangle to a square to a hexagon to a pentagon to a hexagon and so on, and it keeps on increasing all the way until it gets to a circle. So all the roots of unity lie around this circle, where the sum of all the roots and the product of all the roots